Okay, first let's finish the question on the board as an attendance question. It is a calculation for local maximum. So this is one of those questions that we would apply the first derivative. I'll let you to do the calculation yourself because it's one of these questions that we might have done before. We might have completed before. The process will be this is a polynomial. To find a critical point, all you have to do is to figure out the first derivative and set it equal to 0. And then the value that you find out could be the value you find out when the derivative equal to 0 would be the critical point. Using the critical point, you would find point on the number line, determine the interval. For every interval, you will find increasing, decreasing. If it's increasing, then decreasing, you will have a local maximum in between the interval. If it's decreasing, then increasing, you will have a local minimum at the point. So we can determine local maximum or local minimum after we determine the increasing, decreasing behavior. So let's try this. Morning, if you're attending online, please let me know if you can see everything on the screen. Because I was looking at yesterday's recording, for some reason, none of the computer screen material was recorded. So I failed to upload the class recording for yesterday because the material on the PowerPoint was not, or the calculation I did on the board was not recorded. So I don't know what was the reason. All I can do is make sure that you can see everything if you're online. If you don't see, if things are not as normal, please type that in the chat. Or if I was not looking at the Teams app, you should speak out with your microphone. I mean, everyone attending the online class meeting, if one of you detect anything that's abnormal, please let me know. But this is just one of my efforts trying to make sure the class are being properly recorded. But I did hear from one of my students that when the class meeting was normal, but this recording could still go wrong. It has something to do with the Teams app. It's been a little bit acting up where something could go wrong. Right. If the sound is not okay, if the view or the screen is not shared properly, please let me know. Sure, I did. Right, this is the question. I'll let you to do the work yourself. The function is x to the power 3 minus 3x to the power 2. So it's a polynomial of degree 3. I don't know if you're finished, but I turned on the recording just so I turn on the scanner. If you have the answer already, please let me know. Two of you have already submitted, but one of them is wrong. So you want to double check your calculation, see if it's right. Let's see. That's right. Thank you. And check your solution once again. Right. Now I see that you corrected. Everyone's answer is right so far. All 5 answer that submitted is correct. Hope that you can do it independently without me going through the process. So then it actually serve a better purpose. Let's see. Okay, that's right. Thank you. So if nobody noticed any problem, then I assume that it was all okay with sharing the computer screen. We would find the first derivative, which is f prime of x. It's equal to, this is the original function. You bring the 3 to the front, it's 3x squared. Right, then bring the 2 to the front, minus 6x, which equals 0. Setting it equal to 0 in the effort to find the critical point. That'll be the step 1. In order to find the critical point, we should solve this equation. Equation of solving. And in this equation, we see 1 term, 2 term. So the subtraction sign separate the terms. We have 2 term. We want to find the common factor. That would be the 3, 6, and 3. They both have 3. And then there is also the x. They both have x. You factor the x out from the 2 term. And then what we see what we have left. The 3x squared, but now the 3x, we have the x left. There's minus, and there's a 6x. Take out the 3x, we have a 2. Right. After factor out the equation, we now have 2 factors. Normally, because 0 is special, because 0 as a multiplication equal to 0, the factor has to equal to 0. That's the whole reason we would try to factor. So then we have 3x equal to 0. First factor, multiplication, determine the factor. Second factor is x minus 2. We also set that one equal to 0. It's an OR relation, but we each solution will determine the left side equal to the right side. And then solving this equation, we have x equal to 0 from the first equation, and then x equal to 2 from the second equation. That finished step 1, which is determining the point of the critical value. And then step 2, which would be determining the interval. On the number line, you find out 0, you find out 2. So what are the interval? It's negative infinity, 2, 0, 0 to 2, and then 2 to infinity. So those are the intervals, 3 intervals. And then you move on to step 3, and we have to know the increasing, decreasing. The first interval, pick any number, negative 10 is fine, negative 100 is fine. But I would probably would use a derivative at a smaller value. So it's pick negative 1. We put it into the derivative function. You use any derivative. These two, this one and this one, they're identical. They're the same, the equivalent. Whichever you feel easier for your computation. Personally, I prefer the one that's factored because it has smaller number. I don't have to calculate the square. So we would have 3 times negative 1 multiplied by negative 1 minus 2, which is negative 3. Right, as you can see, it's equal to 9. If you multiply out, it's positive. So we know that is increasing there. In the first interval, it's increasing. And then the second interval is between 0 and 2, so we can try to calculate a value between 0 and 2. Let's pick 1. We're going to put it in here, so you go 3 times 1 times 1 minus 2, that's -1. So if you finish the calculation, it's -3. Negative, so it's decreasing. So on the interval 0 to 2 is decreasing. The function is decreasing. The last interval is 2 to infinity. You can pick any number between 2 to infinity, such as 4, well, or 5, or 10, or 3. Anything higher than 2 is fine. Just pick any point to test it. 3 times the x is 4. And then 4 minus 2, 4 minus 2 is 2. So we end up getting a 24 with the derivative value. 24 is positive, so it's increasing. Okay, so that will be the increasing, decreasing behavior. The exact graphs are not going to be this straightforward. There has to be a high relation. You can see it's going to be increasing, decreasing, and then increase, maybe a little bit more curvy. Increasing, decreasing, and then increasing. How it exactly, you will have to calculate more number. So for example, if x equal to 0, what's going on? If x equal to 2, what was the y value? I didn't do any y value calculation, so that's hardly the entire curve sketching process. But by now, you should already see the overall shape of it. And so that will be it. And then over here, you can see at this point is when the 0, this point is at 2. So you can see that 0 is a local maximum, as 0 is a minimum. And let's go back. I hope that you have mostly already answered the question. Okay, so this is the process. I'm hoping that with practice, we're able to do it independently without additional help from the book, from me, from your friend, your neighbor. The whole point of doing all that practice is that ultimately we're able to actually calculate the derivative and use the derivative to figure out the behavior of the function, right? Almost everyone have already submitted answer. Dylan, are you still working on it? Do you need more time? All the solution that was submitted is correct, so I assume that you've been following what we're doing. Any questions? Any questions? I'll leave the scanner open. Please submit your answer, Dylan. All right, other than the bigger question, there's something else I want to talk about. We have scheduled the exam on this Thursday, right, which will be tomorrow. But today when I arrived in the classroom, you guys mentioned that many students feel like you are not ready for the test, right? Right? What do you think? You felt like you're almost ready? Okay, so I certainly do not want to force you to take the exam when you're not ready or when you haven't finished most of your homework. I haven't really updated more grades onto Georgia Review. The grades are still on the WebWork website. Eventually, when we're done, I will try to copy it over. Not most of the time after a test, I will copy over the homework grade because we were supposed to finish all the homework. So I wonder if any of you guys attending online feel the same way, because right now we have the number of students attending online is higher than the number attending in the classroom. So I guess to get a balanced view of the issue, I would like to hear what you think about. Right, if you have any opinion, please voice. Okay, thank you, George. And anyone else? George said you feel like we need more time. Okay, 2, 3, 4. I already have 2 students in the classroom feel the same way online. I see 4 students. agree that we need more time. Okay, so if we're not scheduled the exam for tomorrow, we would have to schedule it for next week. What time next week? What do you think?
Maybe Tuesday or Wednesday, so we would have to learn. Take over,
Okay.
like a weekend where we could have to go to class.
Okay, Tuesday or Wednesday. Richard, what do you think?
I'm good either of those days.
Tuesday or Wednesday next week? Okay, so if we are moving the test to next week, we wanna identify a possible time. Right, so now I have two students says Tuesday and then in the classroom already. What do you think? Tuesday's fine. So that counts for 1, 2, 3, 5 students for what? If this is assume like a polling of the class, so that would be. Okay. So I see 3 in the classroom and 4, at least 4 online agree that Tuesday would be okay for the new test date. So we agree that Tuesday, moving the test to Tuesday would be okay. Okay, so if you're attending online, we're talking about moving the test date to allow more time to study and more time to finish the homework. So if you are concerned or if you don't like having a Tuesday test, please say so during the class so that everybody's opinion can be heard and discussed. So if you feel like want a different day or having a different opinion, please talk about it or write about it online. Anyone have more ideas or opinions? Okay, I don't see any. Okay, waiting. I don't see any different dates being mentioned on the online meeting room and in the class. So let's decide that we're moving the test date to next Tuesday, which is, if my calendar is not wrong, let me try to look at, because occasionally I type up the date wrong online. So let me pull the calendar on my phone. Next Tuesday will be the 8th, April 8th. So the calendar over here. See, that's the problem. I think I type in the wrong date. Next week it is the whole thing before the semester. I think I type it wrong. Okay, so so next week the Monday's supposed to be the 7th, right? And then Tuesday's supposed to be the 8th. I'm trying to. That was a Tuesday. So let's try, that was the past recording from past classes. Let me remove that and also remove this. It looks like our schedule is tighter than last time when I was teaching the same class. But the ultimate goal is to have everybody's homework done. And so that will be our new test day. So April 8th would be, we're gonna schedule for the next test. And in the meantime, please finish as much homework as possible. And I should also change this. The date was originally moved. Actually, you indicate that I sent out a message before, so change it. make sure everybody receive a new email about it, so everyone would know that the testing is. All right, so that's it. So what do we do today? Any question from homework that we should talk about? Yeah, okay. And I have the homework open up. Well, I really wish everything is recorded properly for today because we are making some big decision, or at least more than what we did yesterday. Yesterday's recording was lost. So if you're attending online, it looks like everybody was able to see what's on this computer screen. See how it's, I already set up the recording, but somehow yesterday, I think yesterday I did the same thing, but now nothing was recorded. Only the voice was recorded. There's no computer screen in the recording, so I was really puzzled at what happened. All right, your question was, which one? Number 10.
I'm just a little confused with the natural log.
Okay, you know the derivative of natural log is 1 over x.
Yes.
Okay, let's make this larger and go through the steps. The only thing that's important to us is to identify the function. We will the rest. Right, we're using calculus as a way to understand the function. So then we gotta know the first derivative. We also have to know the second derivative. So before we do the step 1, 2, 3, 4, 6, 7, we gotta have these sets. So first derivative, type it because it looks more organized if it's typed. So the first derivative is equal to these. You can see the function. There's x in the natural log, x in the x square. It's multiplication. So we will apply product rule. According to product rule, we try to type. If you have to multiply, you try to find the derivative. According to product rule, you do one at a time. So f prime g plus f g prime. So that's product rule. Applying product rule to this, we will have the 3x squared should be differentiated. This differentiate. This is multiplied by the natural log function plus, and then we will keep the 3x squared. Again, sorry, to write our notation, and then multiply by the derivative of the natural log. Write a little prime notation to indicating the differentiation process. So that's the product rule applied to this function. Okay, that's before we do the calculation. So we're going to set it up just in the way that the product rule will be set up, and then we're going to start doing the calculation. So I try to separate the calculation from the actual product rule process so that we don't have to think about product rule and differentiation at the same time. So we would set up the product rule and then do the differentiation. Derivative of 3x squared is 6x, right? That is the derivative, and then we have the natural log to carry with it, and then we have this part, and then to make it easy, since we already write that part, just copy it over. Okay, there. So that we still have to find the derivative of the natural log, which is 1 over x. So that part, let's try to actually do the work. So derivative of natural log is 1 over x. 1 over its fraction, 1 over x in the denominator. That will be the first derivative, and we should notice that there's a division, and here we have the x in the denominator. We also have the x in the numerator. They will cancel, right? Cancel the x. This will become x squared divided by x is x, so it's just 3x. Are we okay? Right, so we would set it equal to 0. No, not yet. Let's finish the computation. right? This is equal to, let's try to simplify it. The 6x natural log of x plus 3x, because the x cancel with each other. That's the first derivative. Any questions so far? All right, and then we're gonna apply we're gonna try to find the second derivative. So instead of trying to work on increasing, decreasing, and work on concavity, let's try to find all the derivative before we do any analysis of the function. Second derivative is equal to. At first we start with this. That is a multiplication. There's an x here. There's 2x. There's multiplication between them, so it's product rule. Okay, so we'll do the same. We would take the 6x, which is the first function, and find the derivative times natural log of x. Write it better. And then, or you keep the 6x, but then you will find the derivative of the natural log. It's kind of like almost the same process. Do it again, except the first function is 3x squared times natural log. Now we have 6x and natural log. It's multiplication. Nevertheless, we apply product rule. After applying product rule, we should finish the prime notation indicated more calculation. The first one, we differentiate the 6x, then you get 6. So 6 times natural log of x plus this time you're going to have 6x. And then you have to multiply the derivative of natural log. But derivative of natural log is 1 over x. 1 over x is a division of the x, right? So if you have 6x and you divide by x, it cancels that x. So that's what we have for the second derivative. Any question? All right, so now we're ready. Now let's look at all 3 steps. On web work for this assignment, we would follow the 3 steps. Step 1 is try to determine the domain, and the domain is different from function to function because the domain is asking what is the proper x value that allows you to execute the calculation required in the definition. If the definition only has summation or multiplication, then it's all fine, any number is okay, and the domain will be all real. If the calculation requires division and you will try to set the domain in the way to avoid division by 0, now this calculation has multiplication and a natural log, right? Natural log is the power of the exponential calculation, right? Natural log is defined or invented in the effort of trying to figure out the power in the exponential calculation. So it's the reverse of the exponential calculation. In exponential calculation, the input is any number, but the output is an exponential value. E to any number is a positive number. So the input is any number, output is positive. So for natural log, the input has to be positive, the output is any number, right? The range is all real, the domain is positive number. So because the natural log calculation that we have in the domain, okay, if you want to do natural log calculation, your x has to be positive. So as a domain, we are looking at a domain of 0 to infinity. That is the same thing as x is bigger than 0. This is the two that's equivalent. But the interval notation definitely matches better to the number line, which is why the interval notation is preferred when we represent a set. Right, that's step 1. We know that we're gonna draw our number line like 0 to infinity. We won't do the negative infinity to infinity. We'll do 0 to infinity. Step 2, we're gonna try to determine the increasing and decreasing behavior using the first derivative. But that process actually involves 3 steps in itself. So let's look at increasing, decreasing. In step 2, you're going to take your first derivative, which we already have it. We're going to set it equal to 0. So let me try to write it a little bit better. So we're going to set 6x natural log of x plus 3x equal to 0. Solve for a critical point in this case. And again, as we mentioned before, when we look at the equation that we were supposed to solve, we have to understand the structure of the equation to figure out what is a key information in here. This is a summation in the middle, and all the rest are multiplication, like 6 times x times natural log plus 3 times x. Multiplication is like the glue that will combine the term together. So all the term that's multiplied are considered one term. So this is one term, and that's a second term. Now the plus or minus sign separate term. So essentially we have two terms on the left side of the equation. Between those two terms, they have common factor, which is 3x. Yes. So we're gonna pull the 3x outside the equation. So if you write 3x out, and what do we have left? In the first term, take out 3x, we have 2. We have natural log of x. In the second term, take out 3x. We have nothing left. But as a factor, even if you have nothing left, you still have the number 1. Because 3x times 1 equal to 3x, right? We cannot write 0 because 0 therefore is not a factor. 3x times 0 would be 0. We don't want that. 3x times 1 is 3x, right? So that is a proper factoring process. As before, if you're solving an equation, being able to factor for a 0 on the right side of the equation, that the 0 is a special number where the factor of 0 has to be 0. At least one of them got to be 0. So we're able to separate the big equation into two small equations. 3x equal to 0 is the first one, or the 2 times natural log of x equal to -1 is going to be the second equation. Or you can see it's 2 natural log plus 1 equal to 0, but then I move the 1 to the other side equation. Are you okay? So we're going to solve this. The first equation is easy to solve. 3x equal to 0. 3 is not 0. X has to be 0. And then the second critical point is I have to spend a little bit of time working on getting that x by itself. And this is a logarithm equation. Equation that involves logarithm is called logarithm equation. To solve logarithm equation, the ultimate idea is to do the opposite of natural log. Opposite of natural log is exponential calculation, right? Logarithm is a inverse of exponential calculation. But before we are able to do that, we're going to look through this equation. There's only one x, so your process will be involving peel everything off the x, right? You peel the outside first. So we'll divide both sides of the equation by 2 first, and now here the natural log of x is equal to -1 divided by 2. What is -1 divided by 2? It's -0.5. If you use a calculator, right? When we do that, at least we get the 2 away from the left side of the equation. The 2 is multiplied. That's why we divide both sides of the equation by 2. Any question? And then we have only one thing, which is remove the natural log to get x by itself. And how do we do that? We do the reverse, which is the e, right? We do e of both sides of the equation. You do let me write e of the left side and then e of the right side, e to that power. Are we okay? The natural log and e are inverse of each other. So e to the natural log of x, e and natural log are inverses. And after you do that, the left side actually the x because they cancel. The inverse function cancel each other. So that's the left side. And the right side will be e to the power of -0.5 to the exponent. So that's the solution. Any question? That's our critical point. One is 0. 0 is at the boundary of the number line. That cannot be like any additional point. So we're going to find our interval. Remember in step 2, we're going to determine increasing, decreasing. So the interval is the 0 to infinity. You have your 0. E to the -0.5. You can find the value in your calculator, but it's a positive number. It's supposed to be large, to power 1 to a power -0.5. It's roughly Okay, that's roughly how it is, roughly 0.6 in value. Like roughly 0.6. Because we want to find increasing, decreasing, we have to kind of know how big the number is. So now we have this two interval, 0 to e to the negative 0.5. That's the first interval. We start with 0. The second interval is e to the negative 0.5 to infinity. So those are the two intervals. Then we need to know increasing, decreasing, and we're gonna find the derivative value. So derivative value at that was roughly 0.6 in e to the negative 0.5. We can try positive 0.5, which is equal to calculate this. That's the derivative. We're gonna plug in 0.5 to find out the value, which is typing the calculation and actually put it into a calculator. So first derivative again, 6x is negative 0.5, 6x natural log of x. Oh, it's not 0.5, it's it was supposed to be positive, e to the negative 0.5. And then there's natural log e to the negative 0.5 there. And then plus 3 times e to the negative 0.5. Okay, so that's the entire calculation. As you can see, I'm not calculating it by head anymore because I will be able to do the natural log or exponential calculation by hand. So calculator. We can type this whole thing into a calculator. So I try to type it out. Equal to 0. All right, let me look at if it's a special number as such as E0. Okay, so it is 0. So basically this is equal to 6 times e to the negative 0.5. And then time the natural log will cancel the e, so that is times negative 0.5, and then we plus 3. That's the multiplication. Okay. So the 6 times the negative 0.5, these two multiply will give you negative 3. And there we have positive 3 of e to the negative 5. And here we have negative 3 of e to the negative 0.5. That's why they're opposite. So the total is actually 0. What does that mean? It means the derivative is 0. And then I'm just
I'm questioning why you're carrying over the e into that 6x natural x.
Well,
why would we
because
do 0, the negative 0?
It's not supposed to equal to 0, I suppose, but I find the 0. Yeah. Right. Why do I carry the e? That's a good point. Yeah, we should plug in the 0.5, right?
Yeah.
Yeah. So I did it wrong. I totally confused myself with e to the. It's supposed to be just 0.5. I did e to the something is not working in my brain. Okay, so I did the wrong calculation, which is why it equals 0. It equal to 0 because that was supposed to be a critical point. If I do use that, then of course it will be 0. So it's and of course we were supposed to calculate 0.5. I think that the 0.5 is what's making it confusing. If I do 0.4 or 0.2, it wouldn't have that issue. So yeah, we would do 6x of time natural log of x plus 3x with x equal to 0.5. So there's no e to it. I shouldn't do e to the negative 0.5. It should be a non-zero number. Having it equal to 0 definitely, it's a critical point that should be 0. So I find a negative 0.579. It's a negative number. So negative 0.5 place. Negative 0.579. The exact value is not that important. Being a negative indicating it's a decreasing interval between these two numbers. All right, and then in the second interval, which is to infinity, we can use any value. And to make the computation easier, let's do 1. So we find the derivative value at 1. Typing up I type it wrong first time. So let's calculate. This time we calculate 6 times x equal to 1, and then natural log of 1, and then 3 times 1. Okay, what do we know? Natural log of 1 always equal to 0, so this is already 0, so that we should have value of 3. And of course, you can double check if you put it into a calculator. So I tend to make errors when I'm typing, so double check. It is equal to 3 and it's positive, and that is meaning that in the second interval it will be increasing. So now we finished determining the interval and identify increasing, decreasing on those intervals. We should answer any questions related to the increasing, decreasing behavior. Go back to this question. List any critical point that we find. 0 is not in the domain. I don't have 0 in my solution. That was one of those numbers. But 0 is actually at the boundary, and x is bigger than 0, so 0 is not something we need to consider, even though it is a 0 for the equation itself. So the critical point that we would enter is only 1. So e to the negative 0.5, that's the critical point. The increasing interval, see, it was decreasing, then increasing. So the increasing interval is this one. So it's e to the negative 0.5 to infinity, e to the negative 0.5 to infinity, INF. That was indicated in the instruction, which INF for infinity. And then the other interval will be decreasing. That's from 0 to e to the negative 0.5. That's decreasing. If the function is decreasing, then increasing, we will have a local minimum. So the local minimum happen at x equal to negative 0.5. And you see the behavior, the function goes decreasing, then increasing. And therefore, we do not have a minimum. We do not have a maximum because function will be increasing. And we cannot reach a boundary there. So we would say none. Here, enter none if there's no local maximum. Any question so far? So these are all application of the first derivative. And let's move on to concavity. We have already calculated the second derivative. So in step 2, we were supposed to decreasing, and that will be all about the first derivative. Okay, let's talk about step 3. That is about concavity. Right. We will set the second derivative to 6 natural log of x plus. Type it in writing is awkward looking. So 6 times natural log of x plus 6 equal to 0. So we set the second derivative equal to 0 in the effort of trying to find the concavity, trying to find the inflection point. You would subtract 6 from both sides of the equation. So then 6 times natural log of x equal to negative 6. And we can divide both sides of the equation by 6. We'll cancel the 6. We have natural log of x equal to negative 1. Right, and remember what do we do? We want to solve for x. And how do we get rid of it? Right, you have the x is equal to, we do exponential function of both sides of the equation. So e of the left, e of the right. So it's going to be e to the power of negative 1 that we need to calculate. And try to find the approximate value of this, which should be even smaller, and that was the value needed for estimation. So Okay, so that's the point that we find out, the point we mark on a number line, which would look like this, from 0 to infinity. We identify the e to the -1. And then now you have two intervals, 0 to e of -1, e of -1, e to the -1, actually also. Same thing, -1 power is a division. So that would be the first interval. The second interval is e to the -power 2 infinity. Now we need to know concavity on both intervals. To determine concavity, we will do the calculation of the first derivative, second derivative. So for example, we can calculate second derivative value between 0 to e to the -1. Let's pick a really small number. I'll pick 0.1. Remember last time we picked 0.5. I entered it wrong into the first derivative. I guess I was trying to pick a number that's deviating from all the other number. So we would calculate it with 6 natural log of 0.1 plus 6. So let's try and see if it's increasing, if it's concave up or concave down. So this calculation is roughly negative 7.8. So because it's negative, because it's a negative, we know it's a concave down. So it's concave down. That means it's like this way. That's on the first interval. It's concave down. And then let's see, the second interval. From e to the -power 2 infinity, we calculate a number higher than e to the -1. And it's pretty easy, just calculate the number 1. We'll calculate 6 natural log of 1 plus 6. Now, natural log of 1 or logarithm of 1 all the time equals 0. So this is 6 or 0 plus 6. 6 is positive, so it's concave up. So on the second interval, it actually goes concave up. Okay, so you can see it's decreasing, but concave down, and then concave up, and then pretty much concave up the whole way. That's how the graph is supposed to look like. So we're gonna go back to the solution page, and so we already have the answer to it. All right, so the interval for concave up is from e to the -1 power to infinity. When it's concave down, it was concave down first, like 0 to -1 power. That's the interval when it's concave down. And we have the inflection point we do. That's the point e to the -1 power. And we were supposed to sketch it. All right, to actually finish the sketch, we need to know the y value. I'm going to enter 1 first. And that pretty much, did I find the wrong concavity? Okay, that means the second derivative is wrong. Yes, so I made a mistake in the second derivative, which is right. Yeah, I realized that when I was doing okay, this is a really very obvious mistake. This was I was using the second derivative, so I did the product rule on that, and then this part is giving me this and this. But then I forget to differentiate this 3x, right? I forget to find the derivative of that part, right? I find the derivative using product rule. That was a product rule, right? Sorry, I totally didn't realize I forget to differentiate the 3x. Derivative of 3x is plus 3. So this is a plus 3 that we have, and there should be a plus 3 over here. So this is a plus 3, which makes it 9. So this is actually -9. So in the calculation of the second derivative, I differentiate only part of it and forget to differentiate the 3x. So they divide both side by 6, a natural log of negative 9/6 instead of 6/6. 9/6 is 1.5. That's supposed to be e to the negative 1.5 instead of -1. Okay. So then the critical point is actually happen at e to the negative 1.5, and the +3 change it to a 9, and that will affect how we calculate it. So it should be e to the negative 1.5. I miscalculated the second derivative. That's the question 10. Any questions? I wonder if you guys noticed that when I was calculating the second derivative. Any questions? Was it different on your version,
Can you go back with
the calculation? It was 2 parts in the first derivative. That was the first derivative. The second derivative is supposed to be the derivative of the first derivative, but I differentiated the 6x times natural log of x. I forget to differentiate those 3x. That was the one that's missing. I thought I was careful because I was trying to write slow, but I still forget to do more. Differentiation. Derivative of 3x is 3, but derivative of 6x of natural log of x, we will have to apply product that will having these 2 parts. So it won't actually happen and e to the negative. And the overall shape seems to be consistent. Any question? The actual graphing, we should include all 3 points that we determine. Try to find the proper x value and y value. We find out the e to the x over 0 will be undefined. We have e to the negative 0.5. And then e to the negative 1.5. And we're supposed to calculate the y value to determine the proper behavior and the graphs. So if we're graphing it, sketching it, then we should know the y value for this. So now we're not talking about activity or increasing, decreasing, or using the original function to determine the y value. That would be 3x squared natural log of x. These are the calculation will be 3 times x squared multiplied by the natural log of the input value. Right? We use that. The first calculation will be 3e to the negative 0.5 squared. Natural log e to the negative 5. Try to sketch the graph. So here on the value. If we graph it by hand, so the 0.0. So this one is y value 0.55, and this one is 1.5. Oh, x. Mistake, that was negative. And the first one's wrong. It's a negative sign there. So it's negative. I just want to finish the sketching. So if we intend to sketch the graph, you should try to sketch it Okay, so that was even smaller. Negative 0.224. These are all pretty small. That one, I haven't really calculated this one. This one was roughly 0.6. We were talking about its value. X equal to 0.6 roughly, and y negative 5. And this one is even smaller. In this, instead of equal to -1, we have e to the negative 1.5. The denominator is getting smaller, so it's 0.223. Right. So what will happen if we try to sketch it? We kind of already see the activity and the increasing, decreasing. All we have to know is find the proper points of it. So that's x-axis and y-axis. When the x equal to 0.6, the y equal to negative 0.5, roughly there. And then when x equal to 0.223, y equal to negative 0.4, like that. If x equal to near 0, then that's the original function. This is our original function. At the boundary, x cannot reach 0 because natural log of 0 will be undefined. But natural log, when x take on really small number, the natural log of x will be negative. And if x is near 0, this is also really small. So it's going to be a negative small number. We have a concave down, so it should be all the way concave down. I think it's this way because it's supposed to be concave down and decreasing. And can't figure out the proper behavior there. But this will be increasing, so yeah, I can't really exactly. So it's decreasing before this point is concave down and then start concave up. So starting from this second point, which is this one, try to mark it out, the 0.223 and negative 0.224. This is a concavity inflection point, start concave up. So start from here, it went concave up, and x is really large. See this calculation, if x is really large, the 3x squared will be large, natural log will be large. They're going to go increasing, right? So this way, I think that's how it behave. Try to sketch the overall behavior. So concave down to this point and then increasing. Okay, so the sketch there is, I think before this is all go to negative infinity. So see if it's accurate enough. I mean, if you try to sketch the graph, you have to look at a lot of other stuff. So I think the practice of sketching itself brings some thought process, and you have to think about more about how functions behaving and try to change senses. You and then didn't really change it. Okay. All right. So this is the point when it's so it's decreasing then increasing. The concavity changes. It's hard to find the inflection point. Roughly here, it was concave down and then start concave up. So I didn't realize it's gonna try to reach that point. And that's my mistake because it was a natural log of x. When x near 0, it's really, really small. But compare the smallness. This one is near 0, this one is near infinity, but this one has higher power. So I guess that's why it reaches back to 0. So one of the problems that I was sketching is not exposed. limit there is not right. The limit value on the further left side is near the zero. It should be like this. And then went all the way back. So that's the final version of the sketching. Remove all that to say totally misunderstand the left behavior should reach zero, but negative infinity. Okay, any other question? I guess I finished this question 10. Were you able to finish your version of it? Sorry. As you can see, even if I already have the second derivative and the first derivative, my sketch was still a little bit off on the left end point because I didn't calculate the limit properly. The right side, it went to infinity, so that one was okay. The left side, we should calculate when x approaches zero, what would be the limit of 3x squared natural x. So on the left side is the limit calculation, which is kind of the left side and right side, we have an open interval. So when we see x is bigger than zero, that means say zero is a starting point, and yet zero is not reachable. It's an open interval. So we have to calculate limit of the function when x approaching zero to draw the left side of the function, like limit of 3x squared natural log of x when x is approaching zero, like when x is almost near zero, what happens to the y value? According to the graph, it should be zero. But if you wonder how do I do that calculation, we're going to talk about it in chapter 4. Do a limit computation in a short way. But you can also try calculate this limit with a number, right? You can plug in x equals 0.01, 3 times 0.01 squared times natural log of 0.01. You can see that number is almost zero. So that's one way we can tell that on the left side of the limit is supposed to be zero. That is fully calculated. I was just trying to estimating the number. I thought it would go really, really negative and large, but it's not large, it's zero. That's question 10. Do you want to go over any other questions?
So on the test, are you gonna ask us to sketch our own graph, or are you gonna?
No, it's, as you can see, it's quite time consuming to sketch the graph, and there's a lot of calculation going on with a y value. Probably not like that. Very much quite similarly to the practice question. So more of an understanding of the relation between your derivative and the graph.
Okay.
So very likely I'll give you the graph and you choose a point or you do the graph.
Okay.
For the 5, for 3.5, we focus on the graphing. But all these skills, like the second derivative and concavity is 3.4, and then the first derivative, the increasing and maximum minimum, they were 3.3. So 3.3 has its own homework. There will be 2 questions from that. 3.4 has its own homework, which there's 2 questions already. And that's why on the test, in the last 2 questions, we're not going to focus on the derivative as much because we try to understand the graphs. Yeah, even though in the graphing, we should be doing derivative calculation, but since we have a question that handles derivative calculation in section 5, we focus on more on graphing. That's what I want you guys to try to graph it. And you can see I'm not the best with the graphing, but the more you study the function, the more you have the idea of how the graph's supposed to behave. But it's really dependent on personal experience sometimes. Even I graph it wrong occasionally with either the calculation, if we're not careful, the calculation might be wrong with the plotting the point. Sometimes it's because we perceive the concavity and decreasing the incorrect way. It will affect our graphing. But I feel like the more we graph, the more we understand the relation between the derivative and the graphs. So I think part of the reason for 3.5 is forcing us to study and understand graphs. Any other questions?
Can you look at problem 7?
On the same sets?
I haven't figured out, but are you gonna have a question necessarily like that on the test? Or
Was the 7 hard?
It's just a little confusing.
Oh, okay. Let's see. Problem 7, exactly 2-point label in variable shows the function f, the derivative of f is 0. Second derivative f is not 0, and one select the signs for each with. Okay, as on the graph, you can see these are the 2 point. Well, can't really graph it. Let me copy this so we can draw it. So we're really trying to study the relation between the graph and the derivative, so we can try to find all the derivative for every single point. For example, we start with A. It was like it was decreasing then increasing, right? Remember, whenever the function decreasing then increasing, you have at local minimum, we're supposed to have the first derivative. That's a critical point, right? Okay, so at A, for point, let me try to change the color so it's more visible. For point A, okay, is at a minimum, it was decreasing then increasing. Remember, if it's decreasing, the first derivative would be negative. If it's increasing, the first derivative will be positive. But at the minimum, the first derivative should be 0, right? At the minimum is not decreasing, is not increasing. It's in between the decreasing and increasing. So at point A, we should have the first derivative that equal to 0 for point A. On the other hand, you see at the A, the function when decreasing then increasing. So the derivative is negative and then positive, right? If the derivative went negative then positive, that means the derivative is increasing. If the derivative is increasing, then the derivative of the derivative will be positive, right? Any function that are increasing would have a positive derivative, right? Right? So that's concave up. That at point A, we should have the first derivative equal to 0, but the second derivative gotta be positive. That's because it's concave up. Are we okay? All right, and then let's talk about B. Point B. Right, if you look at B, is it increasing or decreasing? It's increasing. So the first derivative should be positive, right? Positive derivative means increasing. So we would have the first derivative that is positive instead of 0. And then also the second derivative would be, no, it's still concave up, right? This way.
So it's still, okay, yes.
It's the second derivative should still be positive. Right, and that at least is what we can answer for. And also you can see the point B. It is it crossed the x-axis, right? Right. So the y value, the original function is 0, exactly there. So the original function over here is equal to 0. It was a critical point. On the other hand, for A is below the x-axis. This is the x-axis, so it's below the x. It's below the. And so then we actually have the original function that was negative. So I'm trying to go f prime, f double prime for every point. Are we okay? So that's for A and B. I mean, we can follow the tone for all these points. So for A is negative in the original, and it would be 0 for the derivative. It would be positive in the second derivative. For B, it was 0 in the y value, and it would be positive in the first derivative. It would also be positive in the second derivative. Let's do one more. I hope that gave us some idea. Let's look at C. All right. C, what about the original function? Positive, negative, or 0? It's above, right? So the original function should be positive. So we would write f is positive. And what about the derivative?
Yeah, so it should be 0.
It should be 0. So the first derivative should be 0. Now, what about the second derivative?
Looks like concave down.
It's concave down, so it's negative for the second derivative. So that's negative. That finished all about C. And then you can see, let's move on to, let's see, D. You can see it's below the horizontal axis, below the x-axis, so the y value, the f it's negative, so we will have the original function being negative. Now, what about the derivative? Is it decreasing or increasing? Decreasing, so it's negative for the first derivative. Now, what about the second derivative? So it's concave up, so it's also positive, yes. So then this question pretty much asking for each one of this point, we understand all three, the original, the first derivative, and the second derivative. Go back onto that. For example, for D, which said it's negative of the original function, it's decreasing the first derivative, so it's negative first derivative. It's concave up, so it's positive. Right, I only answered 6 of them. You can try to answer the rest of them. Okay, they were like, the one I didn't answer were still blank, but I think the one I did answer was okay. I hope that answered your question. Right, and then think this is a pretty a typical example on how we identify the relation between the derivative function value and the graph. So, any other questions? Okay, so today we changed our schedule for the test. That means tomorrow we are not gonna have a test, therefore we're gonna have a regular class. I hope you guys are still attending properly, but in the meantime, try to figure out any one of the homework are still hard to do, and we try to go over the homework. But if you don't have any question about the homework, we'll go over a little bit of chapter 4 here and there. Because we're a little bit behind the schedule, I worry about not being able to cover chapter 4 and at least some of the chapter 5. That was the plan. So so we try to do a little bit here and there so we don't fall too much behind the schedule. In the meantime, I hope that changing the schedule will help everyone try to complete more homework. I know chapter 3 is kind of hard because we've accumulated of everything we've learned so far. But I think with more practice, do more stuff, graph more. I really feel like even though myself is not the best at graphing, but graphing do give you more of a learning experience. You figure more things as you are graphing. You can use decimals to graph it using the computer and then compare it with your graph. That'll kind of correct any of your misunderstanding, and then that way you get better and better with more practice. Any other questions? Right. That should be most of the stuff that we were talking about today. Try to finish your homework. I'll see you tomorrow with a regular class meeting. There's no test for tomorrow, but let's try to catch up and let's try to make sure we will be on target. I know we're a little bit behind schedule, but try to give me a little bit of time each day to cover a little bit of chapter 4, right? So that we don't fall too much behind. That'll be it for today. I'll see you tomorrow. Thank you.
Will you be sending the homework to
Yeah, I'll reset the homework day to next Tuesday so that the homework will stay open for the weekend. Thank you for the reminder. Yeah, see you tomorrow.